So we're going to look at light bulb with some more power today. Yesterday we started working with power. We saw that the more the voltage, the more the current, the higher the power. You can manipulate that a little bit and get I squared times R to get that, or V squared divided by R to get that power also. But the basic idea, right, is the more the current, the more the voltage, the higher the power. So let's play with that with a light bulb a little bit, right? So I've got a light bulb. One thing I did want to point out, I think I talked about it on one of the simulations, but you have to force electricity to go where you want. So if you look at the way a light bulb's designed, right, especially the old style, right, all the light bulbs are like this. But if you look, you see there's a piece of metal at the bottom. That's where the electricity comes in. Then this black thing is actually an insulator, and then there's a metal again. So that forces the electricity to go in through the bottom, then it goes through the filament, and then it comes out here. So you have to connect on both sides there. Right. And regular household light bulbs are the same way. You're going to have two things where the electricity can go in, then it forces it to go through the light bulb, and then it comes back out. When you develop shorts and things like that, we've kind of hit those ideas a couple of times. It's a bypass where the electricity doesn't have to go through that. What will happen then if you develop a short, since the resistance is very, very low, your current will then become very high, and you'll short the thing out, and it'll quit working. Right? You'll blow your fuse, or you'll just burn up your batteries really quick, or it'll generate a lot of heat and melt stuff and that kind of thing. Anyway, you can kind of see the ammeter here. I'll tell you what the readings are. And you can kind of see the voltmeter here. The voltmeter has these green wires coming off of it. I tried to kind of color code things so you could see a little bit. Let's drop this down a little bit so you can see that stuff better. So the electricity is going to come from the batteries. You've got this white wire here. The ammeter has to be in series with it. Ammeter, again, we think of like grass, really light grass in a river, so it can see how much is flowing past it. So it has to just be very low resistance. The voltmeter, on the other hand, has to be a door or a wall that the electricity can't get past. So I'm going to take my voltmeter and I'm going to hook it up. We need to hook it up on either side of our light bulb. So this will give me the voltage of the light bulb. Just like in the simulation things, whatever I put the voltmeter across is going to tell me what that voltage is there. So if I have 5 light bulbs and I hook it from the beginning of the first light bulb to the end of the last light bulb, it's going to tell me the combined voltage of all of those. If I just want each individual one, I have to measure each individual one, kind of thing, right? I have not connected my series. So as of right now, I have an incomplete series. So there's no light, there's no current, all that kind of stuff. If I hook this to the first battery there, my theoretical voltage is 1.5 volts. If we look, that gets us 200 milliamps, so 0.2 amps. My voltage is negative. How can I have a negative voltage? I just hooked it up backwards, so I'll just flip-flop these guys. And that gets us up to about 0.6 volts, so a pretty low voltage there. 0.6 volts, so if I wanted to know the power, I would just do the 0.6 volts times the 0.2 0.2 amps. It was 200 milliamps, so 0.2 amps. So 0.6 times 0.2 would give us 0.12, right? I get my decimal points on the right spots there. Yeah, so 0.12 watts is all that is. That's pretty low. If I go to a second battery, so now I have 2 batteries, everything died. There we go. We got connection. We noticed once we got connected, we had a gap there somewhere, right? So I spun the battery and got it lit up. You notice the bulb is a little lighter. My current is now up to 270 milliamps, so 0.27. My voltage is up to 2, right? So 2 times 0.27, you're in the range there of what, 0.27, 0.5, 0.54, right? 0.54 watts now. So I increased my current and my voltage, so I increase my wattage. I go up to 3 light bulbs. It's significantly brighter now. We're clear up to 330 milliamps. We're up to 2.5 volts. We go clear up to 4 volts or 4 batteries. We're clear up to almost 400 milliamps, and we're up to almost 4 volts, right? So, and you can see the light bulb got brighter and brighter and brighter each time. I think power tends to be a little bit intuitive for us on those things. So we're going to jump to seeing kind of how we get a few light bulbs in parallel and series and that kind of stuff, and see how that voltage plays out there with those. Switching gears to see how a household circuit would work, and how, rearranging the bulbs in different directions and that kind of stuff. What I want to make sense of is, how does a light bulb work? How do the circuits in the house work? What happens with the power and the current in different locations and that kind of stuff, right? So I think this little simulation should hopefully work pretty well. I wish they would have let me go to whatever resistances I wanted and stuff, because I wanted to do a 60-watt light bulb and it wouldn't let me. So we're going to go with, we'll go through it here in a second. So what I did is I grabbed some batteries, right? And you can, if you click on the batteries on this FET simulation, you can put them to whatever voltage you want. So I made it 120 volts because that's what household voltage is, right? You can also, if you want, for getting used to the circuit diagram stuff, right? We can go to circuit diagram model, or we can go to picture model. But anyway, so I put 120 volts. So this is like your house. Then I hooked it up to one singular light bulb, right? So this is just kind of how a light bulb would be designed to work. If we close the switch, ta-da, we get lights. Now there's no wires to these other bulbs, so we're not worrying about those right at this second. So if I look at the current is 1 amp. So if I want to know what's the power of this light bulb, the power of the light bulb would be the current times the voltage. Well, hopefully I don't have to measure it for you, but the voltage, right, if I go on either side of the bulb, is 120 volts. So the current is 120 volts. So it's 120 watts. Another way I could calculate that would be to square the current and multiply by the resistance. So 1 squared times 120, it's a 120 watt light bulb, right? So this is generating 120 watts. If I did the power here, we would do the same thing. The current times the voltage, it's 120 volts times 1. So the power the battery is using is the same as the power the light bulb is generating. If I hook another bulb up in parallel with it, right? This is the way houses are put together, another bulb in parallel. What we'll see is here. Now, if you notice, let me pull this third light bulb out of the way so we can see this guy a little better. If you notice, the electrons here in this bottom one and the electrons here in this top one do look a little different. Now, my amount of light generated seems to be about the same. So if I hover over this light bulb, it says 1 amp. If I hover over this light bulb, it says 1 amp. They're both 120 ohms. If I hook my voltmeter up to either side, I have 120 volts. If I hook my voltmeter up to this side, I have 120 volts. Remember, voltage splits at the Y, and you can't see it real well, right? But that is a Y intersection right there and right there. So each of those would be 120 watt light bulbs. They would still be 120 watts because their resistances are the same and their voltages are the same. If I look at current, now this current is 2 amps because that's before they split. And then this current is only 1 amp. 1 amp, and then after they recombine, they're 2 amps again, right? So we kind of saw that a little bit last week when we were messing with stuff. You get those higher amperages before and after the splits. So where you would put your circuit breaker is right here where this switch is, because if this switch opens, everything goes. So if you put a circuit breaker or a fuse here that would break at a current of 2 amps, well, when this closes, this has 2 amps going through it, so it would break. If you put it up here, it would not break because it's only seeing 1 amp there. All right, so the more bulbs we put in parallel, each of those bulbs will be just fine, which makes sense because when you have turn your lights on in your house, if I turn the lights on in one room, that doesn't affect another room, right? So I don't know if you can hear that lawnmower, but they are mowing the lawn behind me. Isn't it nice that it's nice out outside now? Nice out. I said out too many times. I'm going to go ahead and move these a little cattywampus from each other. I don't know. Can you kind of tell that that's all in parallel there, right? So we close this. Each light bulb is functioning on its own. Each one's in parallel. There's 1 amp, there's 1 amp, and there's 1 amp. Hopefully you've got the pattern so you can kind of figure out, well, in this wire, it would be 3 amps. In this wire, it would be 2 amps. And in this wire, it would be 1 amp, right? Because they're splitting in those spots. So each bulb is getting 120 watts. Now, before, my battery was producing 120 watts. But if we think about it now, current times voltage will give me my wattage. If I'm doing 120 watts for each of these light bulbs, for each light bulb, the battery is 3, so that should be 360 watts. So the more lights you have on in your house, the more electricity you're using, the higher the power, the higher the power you're using at any given time. Hopefully that's kind of a duh, right? Because we've got multiple things going. So that is how your house is set up. Hopefully that makes some sense. So these would be the true wattage there, right? So I'm going to go ahead and rebuild these guys and say, well, what if we wanted to build our house in series, right? So we're going to go with this guy in series now, and we're going to see what happens to our power. This should be a thing that you could kind of walk through and stuff on your own, but I think it helps to kind of see it to make sense. Because just because we say a light bulb is 100, right? We said these were all 120 watt light bulbs, right? Because that's what they were producing. But if we look at them now, you look at that brightness, that's not the same, right? If I look at the voltage across this guy, I've got 120 volts. So if I've got 3 equivalent light bulbs, I bet you can guess what the voltage is, 40. And then if I go across 2, it would be 80. And if I go across all 3, it would be 120. And my current, right, before it was 1 amp going through everything. Now it's 0.33, right? Because my total resistance is 360. So if we do 120 volts divided by 360, my current is only 0.33. So this is a 120 watt light bulb. But just because it says 120 watts on it, right, that's what the print label would be, is a 120 watt light bulb. It's not producing 120 watts of power right now, because if I do my voltage, which we said was 40, times 0.33, that gives me a 13.2 watt light bulb, and it is producing a lot less electricity, right? And then this one would be the same, 0.33 times 40, so 13.2 and 13.2, so you would get a lot less lights out of that, right? So you wouldn't want to put a whole bunch of light bulbs in series because you would get dropping wattages. But when you put a bunch of them in parallel, you get an increased current in your main wires of your house before they split. And so if that current gets to be too high, it can melt fuses and all that kind of stuff, right? Hopefully that helps. With how household circuits work and stuff. You're going to get a household circuit worksheet to work tomorrow. I don't know if you thought this was too long today or whatever, but I'll put the worksheet on today's and tomorrow's, but it's the same worksheet. It would take too long to do today with it, but we'll do that tomorrow, and then that'll be the quiz tomorrow. So today you won't have a Moodle quiz. You'll just have one tomorrow. Again, if this stuff isn't making sense, jump onto Google Meet, and we can kind of go through a few more of these together. But I think it's important to understand how the stuff in the house is put together, how to figure out what wattages are where, what's going through which wires and all that kind of stuff. You can take household circuits and draw them down to a nice compact circuit diagram and stuff, right? Anyway, have a good one. And there's not too many days left. Let's see. Today is Tuesday the 5th. So you've only got a week and a day left. Ooh, we're going to have to get capacitors in here and stuff too still. So we'll finish up on the 13th because, the seniors got really cryy about having to go 2 extra days. No, I'm just kidding. I get it. Anyway, talk to you later.